After learning the two methods of writing a set, we move on to the different kinds of sets. Welcome to Mathematics of Engineering. Consider set A, which includes all the values of x, where x is a student of class 3913 presently studying in a school. We can go to the school and count the number of students presently studying in class 3913 in the school. Thus, set A contains a finite number of elements. We now write another set B as follows. Set B is the set which includes all the values of x, where x is a student presently studying in both classes 3913 and 3914. We observe that a student cannot study simultaneously in both classes. Thus, set B contains no element at all. A set which does not contain any element is called the empty set or the null set or the void set. According to this definition, and in the previous example, B is an empty set while A is not an empty set. The empty set is denoted by the symbol phi or just the braces. Let's give a few examples of empty sets. Let A be a set of all values of x, where x is a natural number and it lies between 1 and 2. Then A is an empty set because there is no natural number between 1 and 2. Secondly, let B equal to the set of all values of x, where x is a rational number and x squared less 2 is equal to 0. Then B is the empty set because the equation x squared less 2 is equal to 0 is not satisfied by any rational value of x. Thirdly, let C be the set of all values of x, where x is an even prime number and x is greater than 2. Then C is again an empty set because 2 is the only even prime number. Lastly, let D be the set of all values of x, where x is an odd number and x squared is equal to 4. Then again, D is an empty set because the equation x squared is equal to 4 is not satisfied by any odd value of x. Let's consider the following sets. Let set A have the elements 1, 2, 3, 4, and 5. Set B would have A, B, C, D, E, and G. And set C have the elements of men living presently in different parts of the world. We observe that A contains 5 elements and B contains 6 elements. How many elements does C contain? As it is, we do not know the number of elements in C, but it is some natural number which may be quite a big number. A set which is empty or consists of a definite number of elements is called finite, otherwise the set is called infinite. Consider some examples. Let W be the set of days of the week, then W is finite. Let S be the set of solutions of the equation x squared less 16 is equal to 0, then S is again finite. Let G be the set of points on a line, then this time G is infinite. Consider the set of natural numbers. We see that the number of elements of this set is not finite since there are infinite number of natural numbers. We say that the set of natural numbers is an infinite set. When we represent a set in the roster form, we write all the elements of the set within braces. It is not possible to write all the elements of an infinite set without braces because the number of elements of such a set is not finite. So we represent some infinite set in the roster form by writing a few elements which clearly indicate the structure of the set followed or preceded by the 3 dots. Another example would be the set of odd natural numbers. Lastly, with the elements -3, -2, -1, 0, 1, 2, 3, and so forth, this would be the set of integers. All of these sets are infinite. We can also note that all infinite sets cannot be described in the roster form. For example, the set of real numbers cannot be described in this form because the elements of this set do not follow any particular pattern. Let us analyze some examples. State which of the following sets are finite or infinite. First, for the set of the values of x, where x belongs to the set of natural numbers and x minus 1 times x minus 2 is equal to 0. From the equation x minus 1 and x minus 2, we can note down that x is equal to 1 and x is equal to 2. Thus, our set would have our elements 1 and 2, making this set finite. For the next example, a set for all the values of x, where x belongs to a natural number and x squared is equal to 4. Given our equation x squared is equal to 4, we can compute x as negative 2 and 2. However, what we needed for the set would be natural numbers, or that would be the positive integers. So we would have 2 for our set, and this is going to be finite. For the next example, a set for all the values of x, where x belongs to a natural number and 2x less 1 is equal to 0. Checking on our equation 2x less 1 is equal to 0, we find that x is equal to 1/2. Note that for 1/2, this is not a natural number, where our set would turn out to be a null set, and this is still finite. Moving on to the next examples. A set for all the values of x, where x belongs to a natural number and x is prime. The given set is the set of all prime numbers, and since set of prime numbers is infinite, hence the given set is said to be infinite. Another example, a set for all the values of x, where x belongs to a natural number and x is odd. Since there are infinite number of odd numbers, hence the given set is also infinite. Let's differentiate joint and disjoint sets. Two sets A and B are said to be disjoint if they do not have any element in common. For example, let set A be equal to all the values of x where x is a prime number, and let B be the values of all x where x is a composite number. Since prime numbers are so much different with composite numbers, they would not have any element in common, so sets A and B are said to be disjoint. Two sets A and B are said to be overlapping or joint if they contain at least one element in common. For example, let M be equal to all the values of x where x belongs to the set of natural numbers and x is less than 4. Next one, let N be equal to all the values of x where x belongs to the set of integers and it lies between -1 and 4. For the first set, M, we would know that all those elements turn out to be 1, 2, and 3. For set N, our elements would turn out as 0, 1, 2, and 3. Having 1, 2, and 3 common for both sets M and N, then we can say that sets M and N are overlapping or joint sets. Given two sets A and B, if every element of A is also an element of B, and if every element of B is also an element of A, then the sets A and B are said to be equal. Clearly, the two sets have exactly the same elements. Two sets A and B are said to be equal if they have exactly the same elements and we write them as A is equal to B. Otherwise, the sets are said to be unequal and we write them as A is unequal to B. We consider the following examples. Let A be the set of prime numbers less than 6 and P the set of prime factors of 30. Check for equality. Being prime numbers less than 6, set A would have the elements 2, 3, and 5. Set B would also be prime factors of 30, giving us the values 2 times 3 times 5, where set B would also turn out as 2, 3, and 5. Thus, we can say that set A would be equal to set B. Note that 1 is neither a prime or composite number as analyzed from the fundamental theorem of arithmetic. It states that every positive whole number can be written as a unique product of primes. A set does not change if one or more elements of the set are repeated. For example, the sets A, 1, 2, 3 and B, 1, 2, 3, 3, 2 would be equal since each element of A is in B and vice versa. That is why we generally do not repeat any elements in describing a set. Let's consider the next example. Check for equality of the sets. Justify your answer. Consider set X as the set of letters in alloy, set Y the set of letters in loyal. Checking on our elements, we would have A, L, O, Y, which would be elements for set X as well as set Y. Thus, we can say that X and Y are equal sets as repetition of elements in a set do not change a set. Setting on with our next example. Check for equality of the sets. Justify your answer. Consider set A, which would include all the values of n, where n belongs to the set of all integers, and n squared is less than or equal to 4. Set B would include all the values of x, where x belongs to the set of all real numbers, and x squared less 3x plus 2 is equal to 0. Checking on our equations, n squared is less than or equal to 4, and checking all the integers, we would say that set A would have the elements -2, -1, 0, 1, and 2. For set B, having the equation x squared minus 3x plus 2 is equal to 0, we can have this expanded into x minus 1 times x minus 2 is equal to 0, giving us our real numbers, which would be elements of set B as 1 and 2. Checking that 0 belongs to set A, but it does not belong to set B, we can say that set A is not equal to set B. Considering the last example for equality of sets, from the following sets, find a pair of equal sets, if any, and give reasons. Set A is equal to 0. Set B is equal to all values of x, where x is less than 15 and x is less than 5. Set C is all values of x, where x less 5 is equal to 0. Set D is all values of x, where x squared is equal to 25. And set E is equal to all values of x, where x is an integral positive root of the equation x squared minus 2x minus 15 is equal to 0. Let's analyze each of these sets. 0 belongs to set A. Set B will be null as there isn't any number which is greater than 15 but less than 5. Set C would be yielding us the answer of 5. Set D would have two elements, that would be 5 and -5. And set E would also be giving us the answer of 5. Checking on the results, we can say that sets C and E are equal. Before moving on to the next kind of set, we discuss the cardinal number of a set. The number of distinct elements in a given set A is called the cardinal number of A, and this is denoted with the letter N and close in parentheses the set A. Let's have an example. Let A be the set of all the values of x, where x belongs to the set of natural numbers. X is less than 5. With this, we would find all our elements for set A as 1, 2, 3, and 4. The cardinal number of set A would be given as 4. Another example, let B equal to set of letters in the word algebra. We would note that set B would have elements A, L, G, E, B, and R. The cardinal number of set B would give us 6. The next kind of set is what we call equivalent sets. Two sets A and B are said to be equivalent if their cardinal number is the same. That is, cardinal number of set A is equal to cardinal number of set B. That would be denoted with this arrow. We can say that set A is equivalent to set B. Let's have an example where we consider set C as 1, 2, and 3. Set D would be letters P, Q, R. The cardinal number for set C would be 3, and the cardinal number for set D is also 3. Thus, we can say that C is equivalent to set D. Moving on to unit sets or singleton sets. A set which contains only one element is called a singleton set. Consider these examples. Let K be the set of all values of X, where X is neither prime nor composite. As discussed earlier, there is only one number which we consider neither prime nor composite. Thus, we can say that set K is equal to 1. Let set J equal to all values of X, where X belongs to the set of natural numbers, and X squared is equal to 4. In this case, complying with the two conditions, we can say that the value for set J is just equal to positive 2. For the last example, let set L equal to all values of X, where X is an even prime number. We would say that only 2 is the element for set L. A universal set is a set which contains all the elements or objects of other sets, including its own elements. It is usually denoted by the symbol U. There is no formula to find the universal set. We just have to represent all the elements in a single set, which is collectively called a universal set. One fact, there is no standard notation for universal set symbol. Let us say there are 3 sets named as A, B, and C. The elements of all sets A, B, and C is defined as A, given as 1, 3, 6, and 8, B, 2, 3, 4, and 5, and C, 5, 8, 9. Find the universal set for all the 3 sets A, B, and C. By the definition, we know the universal set includes all the elements of the given sets. Therefore, universal set for sets A, B, and C will be given as 1, 2, 3, 4, 5, 6, 8, and 9. From the above example, we can see that the elements of sets A, B, and C are altogether available in universal set U. Also, if you observe, no elements in the universal set are repeated and all the elements are unique. Consider 2 sets X and Y, where X would be the set of all students in school and Y would be the set of all students in the engineering building. We note that every element of Y is also an element of X. We say that Y is a subset of X. The fact that Y is a subset of X is expressed in symbols as the symbol stands for is a subset or is contained in. By definition, a set A is said to be a subset of a set B if every element of A is also an element of B. We may note that for A to be a subset of B, all that is needed is that every element of A is in B. It is possible that every element of B may or may not be in A. If it so happens that every element of B is also in A, then we shall also have B is a subset of A. It follows from the above definition that every set A is a subset of itself. That is, A is a subset of A. And since the empty set null has no elements, we agree to say that null is a subset of every set. Let A and B be 2 sets. A having the elements 10, 20, and 30, and B with 5, 10, 15, 20, 25, 30, 35, 40 for its elements. If A is a subset of B, but A is not equal to B, then A is called proper subset of B, and B is called the superset. Let's take some examples. Consider the sets null, set A with 1 and 3, set B with 1, 5, and 9, and set C with 1, 3, 5, 7, and 9. Insert a symbol between each of the following pair of sets identified. First, between null and B. Null would be a subset of B, as null is a subset of every set. Second, between sets A and B. A is not a subset of B, as 3 belongs to A, but it does not belong to B. Third, between sets A and C. A is a subset of C, as 1 and 3 belongs to A and also belongs to C. Lastly, between set B and C. B is a subset of C, as each element of B is also an element of C. Consider set A with the elements 1 and 2. Let us write down all the subsets of set A. We know that null is a subset of every set, so null is a subset of A. We see that 1 and 2 are all subsets of A. Also, we know that every set is a subset of itself, so 1 and 2 is also a subset of A. Thus, set A has in all 4 subsets: null, 1, 2, and 1 and 2. The set of all these subsets is called the power set of 1 and 2. The collection of all subsets of a set A is called the power set of A. It is denoted by P enclosed with the name of the set. And every element is a set. Checking on the cardinal number of the power set of A, we have 4, which is equal to 2 squared. This would be taken generally as if A is a set with n enclosed A is equal to m, then it can be shown that the cardinal number of the power set of that set is equal to 2 raised to m.